Hi, welcome to Chapter 3. In Chapter 3, we will be studying work, power, and energy. Chapter 3 is broken up into two parts. In this first part of the video lecture, we'll look at work, power, and energy. And in Part 2, we'll look at the work-energy theorem and the conservation of energy principle. So let's start our discussion here with the concept of work. In physics, work is defined as the force applied times the distance the force acts. And this is a little bit oversimplified definition, but for right now, it's good to get the general concept. So we can think of work as calculated as force times distance. And we'll qualify this a little bit more shortly when there are angles and things like that involved. But for right now, we're going to use this definition here. The unit of work is the Newton meter, because we can see that force is measured in newtons and distance is measured in meters. Now, a Newton meter is a very important combination of units. It's the unit for work and also the unit for energy. And so we will call a Newton meter a joule. And that's abbreviated with the letter J, and that is named after James Joule, the English physicist who was one of the pioneers in the work on energy and thermal energy. So let's just start with a simple example here. Suppose I push a cart using 20 newtons of force for 5 meters. Okay, so here I am, or here you are, pushing this cart. To figure out how much work you just did, you just take the force, 20 newtons, and multiply it by the distance, 5 meters. 20 times 5 is 100. So the answer is 100 Newton meters, but of course we know now that a Newton meter is a joule. So the amount of work done was 100 joules. One of the important applications of using calculations involving work is when the force is used to lift an object up. So how much work do we do when we lift an object? Well, we have to figure out, the force and the distance for lifting something, because that's how we calculate work. So the force needed to lift an object is just the object's weight. So if we think about, this box here in our hand, and let's say we're going to lift it off the floor some height h. Well, in order to lift this box, we have to push with at least as much force as the weight of the box. And of course, the weight of the box is mg, where m is the mass of the box. So and then the distance that we're going to lift, the object or move the object is the height here. So work is force times distance. The force, remember, is mg, the weight, and the distance is h, the height. So the work done to lift something is equal to mgh, the mass of the object times g, which is 9.8, times the height of the object in meters. So here's a simple example. How much work is done if you lift 10 kilograms up 2 meters? So work is equal to mgh. So we have 10 kilograms times 9.8 meters per second squared times the height is 2 meters. And multiplying all these together, we come up with 196. And again, all these units here, they equate to Newton meters, or more simply, they equate to joules. So as long as we use the mass in kilograms, g in meters and seconds, and the distance in meters, we will have the correct units. So the amount of work done was 196 joules. One very important and practical application of work is that of simple machines. A simple machine is a mechanism that does the work needed to move an object by exchanging force for distance. So this will become more clear shortly when we look at some formulas here and also work out and look at a couple of examples. Basically, the idea here is that the work that we put into this machine is equal to the work output of the machine. Another way of saying this is we can only get out as much work as we put into this simple machine. All right, physicists sometimes say there's no such thing as a free lunch. All right, we can't get We can't get work for nothing. But we can use and exploit the definition of work to kind of do a little trick here and turn this simple machine into a force multiplier. So remember, our definition of work is force times distance. So the work put into the machine, this is the work that the person using the machine is going to do. They're going to typically input a relatively small force, all right, because our muscles are only so strong, but we're going to move the machine over a large distance, all right, and so this is going to produce some amount of work. Now we can get the same work out, but what the machine does is it basically exchanges force for distance. So what we're going to get out is a very large force but what we pay for is that the object is going to move only a small distance. So this term here, the force is going to be large and the distance is going to be small. So this is an example of what is called force multiplication. So there are lots of examples of simple machines that you're already aware of. For example, levers, ramps, pulleys, gears, wrench, screwdriver, a hydraulic lift, a car jack, and you might be able to think of some more. We'll look at this, an example in the next slide. The great Greek mathematician Archimedes is supposedly said, "Give me a lever long enough and I can move the earth." So what did he mean by that? Well, he understood the basic mechanisms of a lever. And the idea here is that you can see in the animation down here, we have this guy here, and he's able to lift a very heavy weight over here. All right, it's got a 1 ton, that's a 2,000 pound weight. Now, how can he possibly do that by just pushing down with his arms like that? Well, he's getting leverage, which is, comes from the word lever here. But let's take a look and see how this works from a work standpoint. So the idea here is we're going to push on this side of the lever with a relatively small force, just as much as we can push with our muscles. But we're going to move this side of the lever a large distance. Notice how he's moving this lever down a fair amount of distance. On the other side of the lever, what happens here, and these are due to torques balancing and so forth, is we get a much, much larger force, but we get the price we pay is that the object only moves a short distance. But a lot of times that's all we want to do. For example, if we want to jack up a car, we're going to move the jack quite a bit on this end. We're going to maybe keep pumping it up and down, and the car may just move up a couple inches, but that's enough so that the tire lifts off the ground and we can change a flat tire or something like that. So again, this is the idea of force multiplication. We're basically trading off force for distance. Another example of a simple machine that you're probably familiar with is walking up a ramp is easier than going up steep stairs. Now, you're still doing the same amount of work, but you're just increasing the distance so that the force on your legs is less because the ramp is less steep. Let's now talk about power. In physics, power is the rate at which work is done. So power is calculated by the total amount of work done up here divided by how long it took to do the work. So power is work divided by time, or P is equal to W over T. So we're going to use P for power here. Now the unit of power, remember, work is measured in joules and time is measured in seconds. So power is measured in joules per second, and a joule per second has its own unit because it's so important and shows up so much that it's called a watt. And the watt was named after the famous Scottish physicist James Watt, who invented the steam engine and basically improved the steam engine and started industrial engineering and so forth. So let's look at a simple example here. What is your power output if you push a cart with 30 newtons of force across the room 5 meters in 3 seconds? All right, well, to figure out power, we need to figure out how much work you do, and that's force times distance. And then we're going to divide that by the time, how long it took to do the work. So the force was 30 newtons. The distance was 5 meters. So 30 times 5, that's 150 joules. All right, that's on top. And it took 3 seconds to do this work, we were told. So 150 divided by 3 is 50. And our units are joules per second, or we say 50 watts. And by the way, the abbreviation for watt is an uppercase W. So we can just write our answer as 50 W for watts. Let's look at another powerful example of calculating power. So this one's a little bit different. A 50-kilogram woman runs up a flight of stairs 5 meters tall in 6 seconds. What was her power output? Well, if we think about what's happening here, when you walk or run upstairs, what you're basically doing is lifting something, right? And of course, you're lifting yourself. You're lifting your entire weight up some distance, some altitude or elevation here. That's the height of the stairs, which we're told was 5 meters in this problem. So remember that we can calculate the work done when lifting is equal to, force times distance, but remember it's equal to mgh. So her mass is 50 kilograms, g is 9.8, and the height is how far she lifted her body up, and that was the 5 meters, the height of the stairs. So these three numbers multiply together to get 2,450 joules. So that's how much work she did. Now to calculate power, of course, we need to divide the work divided by the time. So we have 2,450 joules divided by 6 seconds, and that gives us a power output of 408 watts. Let's start by talking about kinetic energy. So what is energy? Well, we have a couple of definitions here that we're going to work with. The first one is sort of a non-technical definition, but we can say that energy is the stuff that is transferred when work is done. Now, what do we mean by that? Well, let's take a look at this animation here. We've got the guy that gives this shopping cart a shove. He pushes it and it rolls across the store. So basically what he has done by pushing on the cart, he has done work on the cart. And what happened when he worked on the cart is he transferred something to the cart that it didn't have before. And that something is energy. So that's what we mean that energy is transferred when we do work on an object. Now, we could take this a step further and think about what does this moving cart do as it rolls across the store? Well, imagine this cart bumped into another cart that just happened to be sitting there. Well, our moving cart would then do work by creating a force and pushing on this cart. And therefore, by doing work on the second cart, it would transfer energy to the second cart. So this is sort of a functional definition of energy. Energy is the ability to do work. And this is really the important and practical definition of energy, because this is the way we use energy in our daily lives. When we eat food for energy, that food energy gives us the ability to do work. When we put fuel in our car, that fuel then has the energy which has the ability to work so that our car can drive and so forth. So the first type of energy that we encounter here in this course is called kinetic energy. And kinetic energy is the energy due to motion. The word kinetic means moving. So kinetic energy is abbreviated by the letter K, and it can be calculated as 1/2 times the mass of the object times the velocity of the object squared. Now, if you're wondering where this formula comes from, I'll show you briefly on the next slide, but we're not as interested in the derivation of this formula as just being able to use the results here. So kinetic energy, or all types of energy, interestingly has the same unit as work, and that is it is measured in joules. And there's a reason for that that will become more apparent later. So let's do a simple example here. What is the kinetic energy of a 150-gram baseball thrown at 30 meters per second? So we know that kinetic energy, K, is equal to 1/2 mv squared. So we have to make sure that the mass here is put into kilograms to use our equation up here. So 150 grams is 0.15 kilograms because there are 1,000 grams in a kilogram. And then we take the velocity, which was 30 meters per second, and we have to remember to square that here. So, 30 squared is actually 900, and then we multiply that by 0.15 and then by 1/2 or 0.5. And we come up with a kinetic energy of 67.5 joules. If you're interested in learning where the formula 1/2 mv squared comes from, this slide here shows just a sort of through an example how you can calculate and derive this result. I'm not going to go through it here because, again, this is not super important for what we're going to do in this course, but it's a pretty straightforward derivation. Basically, I start with an example of pushing a chair for 3 meters using 100 newtons of force. So we know that work is force times distance. We can use Newton's second law and relate force to mass and acceleration. We also know some kinematics. The distance something moves that's accelerating is given by 1/2 at squared. So kind of putting all these three formulas together, substituting them into each other, we end up with that the work that we did here, the 300 joules of work, is equal to 1/2 mv squared, where m is the mass of the chair here and v is its speed. So this is one of several ways that we can derive the result. Let's next change gears here and talk about a different type of energy called potential energy. So potential energy is an energy that's due to position, not due to its motion. So this is something completely different. So not only moving objects have energy, and remember, energy is the ability to do work, but any object that has height, in other words, it's lifted off the surface of a floor or a table or the ground or something like that, can also do work if it were to fall. So if we think of this situation here, we've got this rotating cylinder and we've got a hanging mass here with a string that's wrapped around and around the cylinder. So and this mass is a height h above the ground. So this mass here, if we let it go, it's going to pull obviously on the string and it's going to start to turn the cylinder, right? And as long as while this mass is falling, the cylinder is going to start turning and accelerating. So what's happening here is this hanging mass has the ability to do work, because think about what's happening here. This cylinder is given rotational kinetic energy. And remember, energy is the ability to do work. So energy here, if we think of it as force times distance, how much force can this hanging mass exert? Well, it exerts its weight, which is mg. So that's the force. And what is the distance over which this force can act? Well, it can fall a height h. So the energy in this object here is equal to mgh. Now the question is this energy, mgh, kinetic energy? Why or why not? Well, it's not kinetic energy, because before we let this thing go, there's no kinetic energy at all in the system. Nothing is moving. So this is a different type of energy. The energy of this hanging mass here is due not to its motion, but due to its position, due to the fact that it is off of the floor here by a height h. The type of energy that we introduced in the last slide is a new form or type of energy called potential energy. Potential energy is stored energy due to position, not motion. So this is very different than kinetic energy. In particular, what we looked at on the last slide and what we will mostly be working with in this course is gravitational potential energy. And we saw that gravitational potential energy, or PE, is calculated by mgh, where m is the mass of the object, g is the acceleration due to gravity, 9.8, and h is the height of the object off of the floor or the ground. So let's do an example here. How much potential energy does a 1 kilogram block of metal have if it's lifted 2 meters above the floor? So the potential energy is equal to mgh, and the mass is 1 kilogram, g is 9.8, the height is 2 in meters. So this is just 1 times 9.8 times 2, which gives us 19.6. And again, the units for all types of energy are joules. So that is our answer, 19.6 joules. There are many other types of potential energy that we're really not going to be dealing with in this course, but I just wanted to go through some of them here as we may mention them briefly. Elastic potential energy is the energy stored in a stretched or compressed spring, rubber band, or bungee cord, or anything that can be stretched or compressed. So if you think about that, when you take a spring, for example, and you squeeze it and compress it, that spring now has potential energy stored in it. That spring can release that energy if you, for example, let go of the spring. It can, push something or do work. Likewise, a rubber band. When you stretch a rubber band, you're actually storing elastic potential energy in the rubber band. And maybe you've had fun playing with rubber bands where you stretch it on your finger and then shoot it across the room. Basically, what's happening there is that elastic potential energy that was stored in the rubber band is being released and converted into kinetic energy. Electrical potential energy is a very important form of potential energy, and this is where electrical forces between charged objects do work. We will be talking about electricity later in this course. Likewise, there is magnetic potential energy. There is chemical potential energy, and this is forces due to molecular bonds that are storing the energy. So one example of chemical, or a couple examples of chemical potential energy, are the food that we eat. Basically, we get that energy from the food, from the potential energy stored in those bonds, in the sugars and carbohydrates and so forth. And then also batteries. When we charge up a battery, we're basically storing you can think of it as electrochemical potential energy stored in the battery. Nuclear potential energy, we will be talking about the nucleus of the atom later on in this course, and there is a tremendous amount of potential energy stored in the nucleus, and that's why the nucleus can be tapped, for example, in a nuclear power station. The last concept we're going to talk about in this part of the lecture is total mechanical energy. So let's imagine this scenario here. This is a ball up here. It could be like a baseball or something like that. And notice it's off the ground here and it's flying through the air, after it got hit with the bat or whatever. So the question is, what kind of energy does this ball have? Okay. Well, let's not include thermal energy right now. Let's just talk about what's called mechanical energy. This ball has two types of energy. It has potential energy because it's off the ground, and it also has kinetic energy because it's moving. So added together, this gives us the total energy of this ball. So the definition here, total mechanical energy, is the sum of kinetic energy and potential energy. All right, and so what is mechanical energy? It's kinetic and potential energy, but not thermal energy. Okay, that's something different than mechanical energy. So total mechanical energy here is 1/2 mv squared, that's kinetic energy, plus mgh, that's the gravitational potential energy here. So in our last little example here, describe the total energy of a dropped ball. So here we see our ball falling from rest up there down to the bottom. So at the top, the ball only has potential energy, mgh, right? It doesn't have any kinetic energy until it starts to fall. When it's kind of down in the middle, right, in this position here, it has both kinetic energy, 1/2 mv squared, and it has potential energy, mg, and I said h over 2, because remember, this is the total height of the ball at the top. So in the middle, its height is half of h, so it's h over 2. And also its velocity here, I called it v sub mid, meaning that whatever the value of speed is right here, that would be the velocity we would plug in here. Now, when the ball gets to the bottom, it doesn't have any potential energy because it doesn't have any height. So all of its energy is now kinetic energy. So its total energy would be given by 1/2 m v final squared, where v final is the speed of the ball right as it hits the ground here. So that is our introduction to energy in this part of the lecture. In part 3, we'll look at the relationship between work and energy and how they can be used working together in the work-energy theorems. I'll see you in part 3.